Yes, ma'am. So, yesterday we have discussed about the Newton's second law of motion, which states that rate of change of momentum is directly proportional to, yes, anyone, is directly proportional to force applied. Have you all learned it? Yes, Rudranesh, can you tell me what is the second law of motion? The rate of change of momentum is, Rudranesh, can you hear me?
Hello, ma'am.
Yes, Rudranesh. Can you tell me what is the second
Hello,
law of motion?
ma'am. Hello,
Yes, Rudranesh. Are you able to hear me?
hello, ma'am. Ma'am, no, ma'am. It's a little bit stuck.
Okay, that's fine. So, yes, anyone from you? Harsh, just 1 second. Okay, I'm unable to unmute you. So, Newton's second law of motion states that the rate of change of momentum is directly proportional to force applied. Directly proportional is nothing but it means that when one thing increases, the other also increases. The speed is directly proportional to distance. When distance is more, when distance increases, then the speed also increases. So I ask you to write down this second law in your book. I hope you all have written it. So we'll have a look at the video. We'll have a look what this second law actually is and what is the example.
Second law. As we know from the first law that to overcome the inertia of an object, we have to apply unbalanced force. Newton's second law talks about how fast an object would move. Well, it states acceleration of an object depends on the mass of the object and the amount of force applied. In mathematical terms, Newton's second law states that force is the product of mass and acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. Look at these two swings. If you apply the same force on both swings, check whose goes faster. Let's first push the little kid. See? It goes very high. Now push this fat man with the same force. See, it does not go far, because it has more mass than the little kid. So the more mass there is, the force required to push the object is also greater. Let's look at the mathematical formula of the second law again. It's the product of mass and acceleration. We've already learned that if there's more mass in an object, to move it, we need more force. Now let's see this kid sitting in the swing. If we apply little force, then it goes a small distance. Now if we apply a lot more force, it goes very high. So to get more acceleration, we need to apply higher force. So now you can understand the relation among force, mass, and acceleration.
Good grammar and spelling.
Yes, sure. So I hope you're
Can see, ma'am.
okay, that's fine. Mute everyone.
Hmm?
Hey!
Hmm.
Okay.
Can you stop the first, please? I joined late. I rejoined mom on the Peter.
So this law states that force is directly proportional to rate of change of momentum. So what does this mean? Force is directly proportional. How we can write this momentum? Here, rate of change of momentum, it depends. Rate of change of when we are moving one rock from one place to another. When it is moving, then we'll measure the distance till where it was there in the initial stage and till where it is moving slightly. I'll just show you. Suppose you take a big rock here. Just one second. You take a big rock, it is kept here. So now you are trying to move it. Oh. So here is a big rock. So you're standing here and you're pushing this one. So it has been moved from here. It has been moved from here. It has been moved from a distance from here. You have brought it till here. You have moved it till here. Let it assume it to be a distance moved, like 1 meter. You have moved it. So you have moved it. So you'll measure the distance. Now this movement will be occurred in a particular time you're moving in the given like in 2 minutes or 5 minutes, you're you're keep on putting the force, you're trying a lot, then it took 5 minutes to you. So the change in momentum by time, so it depends, force you are applying, it depends on change in movement, change the position, movement in the sense the change of movement where the rock is moving, the change in momentum by time, what is the time taken. So here force is directly proportional to final movement minus initial movement. So the final movement is this one. This is the final movement where momentum, and this is the initial stage where it was there. Final momentum minus initial momentum. So it can be written as, final momentum can be written as mv, and initial moment can be written as, initial momentum can be written as mu by t. So you can represent these in the form of a formula. So later on, now what we are doing here, we are writing as F is directly proportional to, we are taking off this M. We are taking M as common. We are taking M in common because both have M. Both have M in their formula. So both right side and left side. Final momentum also have mv, m in common, and initial momentum also have mu, m in common. We'll take m here in common. We'll remove it outside and then we'll write in brackets what is remaining, v minus u. V minus u by t. Okay, so this is the formula which we use for rate to define rate of change of momentum. Okay, this is the second law of motion. So formula has been given. So whatever if you are getting any problems to write, if you are being asked to write a problem, so in that problem the digits will be given to you. Suppose the time will be given to you or the force applied will be given to you. So the particular amount of numericals will be given to you. So depending on that, you need to enter those numbers. Final momentum, if it is given, and initial moment, if you have to find out. You have to find out. So I'll show you examples. So how you'll get the problems in this. So this was about the second law of motion. Depending upon this formula, we have to do the problems. So I'll explain you the third law of motion. You need to remember this formula. Now, because you are in 6th grade, in your higher grades, you will be given the problems to solve based on this formula. Okay. Now, there are no problems for you regarding there is nothing given to you. How to use this formula, you'll be learning it in your higher grades. Now just note it down. Record it. So Newton's third law of motion states that equal action has an equal opposite reaction. For every action, there is an equal and opposite reaction. So here, I'll show you one video. What is the action which is being taking place and what is the reaction force which is taking place. Suppose, for example, I'll just tell you. If you and your friend are playing, with a rope. Here you can see. So you are pulling the rope from one end and your friend is pulling the rope from another end. So you are trying to pull your friend. So you don't want to defeat. So you want to pull him and you want to win the game. You both are playing a game that you want to pull that rope and you want to draw a line in between and pull your friend, let him cross that line. Then you'll be the winner. So here you are pulling that rope. You are putting a force to pull your friend towards your side. So you are putting a force. For that force, there is an equal and opposite reaction. What is the reaction? Your friend will also pull that rope. He will also try to pull you towards himself. So there is an equal and opposite reaction. So we'll see the video. What are the few more examples we'll try to see to understand this?
Three.
Second law. Till now, we've only learned the first and second laws of motion. Oh, you're riding a bicycle. Have you ever wondered why a bicycle moves forward? Ah, well, it moves according to Newton's third law, which says that for every action, there is an equal and opposite reaction. To understand this, see what happens when you drop a tennis ball. As the tennis ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball with the same force, but in the opposite direction. Action, reaction. Together, the floor and the ball form what's called the action-reaction pair. So now how it applies to your bicycle. When you push the pedal, the parts of the tire which touch the ground push it backwards. The ground also pushes the tires forward with the same force. So the parts of tires and earth form a pair of action and reaction. So what happens to the earth when your tires are applying force to push it back?
Yes, I'll just play it in a moment. Please switch on your cam, everyone. Ashwin, Ronik, Bhuvan, switch on your cam, everyone. Joshit, Rudranish, Harshit, Teja. I just want to check what you all are doing.
Ma'am,
Manogna.
time is up, ma'am.
Manoj,
Ma'am, I am eating, ma'am.
okay, that's fine.
Backwards.
Time is
Huh?
over.
Oh, nothing happens to it, since the earth is very big as compared to your bicycle. The force applied by your tires does not move it backwards, but force applied by the earth pushes your bicycle forward. So now you understand Newton's third law. Yep, the tennis ball is the right example. The ball and the floor are creating a pair of action and reaction.
Ace JEE or NEET exams with Byju's classes.